This video is just going to run through the work solutions for the multiple choice questions on the 2014 practice SAC for networks. Okay, so here we've got question 1. How many edges does a complete graph with 17 vertices have? So the key word here is complete graph, which means we're using the formula where complete graph with n number of vertices is n bracket n minus 1 over 2 edges. So in this case, that would give us 17 times 16 over 2, which gives us 136 edges, so D. In our second question, we have an Euler path for the network shown above is, so obviously with an Euler path, we know that we need to use every edge once. So immediately we can knock out a couple of incorrect answers. So obviously A and C are too short. Also, we want it to be a path, so we want to make sure that it starts and ends at an odd vertex. So if we look at the graph here, A has a degree of 3, so it's an odd vertex. C has a degree of 4. B has a degree of 4. D has a degree of 3. E, degree of 4. F of 2. So we know that the graph has to start and or finish at A and or D. So looking at the options we've got left, that means we can knock out D, and then we just use trial and error to check which of the two remaining paths work, and we end up with B as our answer there. For part C, a Hamilton path for the network shown above. So again, a Hamilton path needs to use every vertex just once. So we're looking at our keyword there. And we know that D and E are too long. We can also see in C, it actually uses vertex E twice, so our only possible answer there is A. But we can again, through trial and error, check those possible answers. Okay, question 4 is asking us to do a allocation. So we want to allocate to minimise the time taken the cost in completing all 4 tasks. So we need to use our Hungarian algorithm here. Okay, so from the first step, we're going to minus the lowest number from each row. So the first row, we're going to minus 17. The second row, we're going to minus 18. The third row, we're going to minus 25. And the final one, minus 26. So I'll just do our answer here, our working here. We'd end up with 8, 13, 0 and 5 in that top row. 1, 4, 0 and 8 in the second, 7, 3, 0 and 10 in the third row, and 0, 1, 4, 2. Now we can see there isn't a 0 in every row and every column, so we need to go to the next step. So we're going to subtract the smallest number from each column this time. So 0 from the first one, so nothing changes, minus 1 from the second column, 0 from the third column, and minus 2 from the fourth column. So our second step will give us just the same values in the first column, so 8, 1, 7, 0. The third one, we'd get 12, 3, 2, and 0. Third column, numbers stay the same, so we're subtracting 0. And fourth column, we're minusing 2 each time, so 3, 6, 8, and 0. So now we can see we've got a 0 in each row and column, so it's time to check our allocation by drawing the lines. So remember, we need to use the minimum lines to cross out the zeros. So I can actually cross out through here and here. Now I'm only using 2 lines. To allocate 4 tasks, I must use 4 lines. So I need to continue the process. So I'm going to take away the smallest uncovered number. So in this case, that would be minus 1 from everything in that matrix. So if we just try and squeeze it in here, that would give me 7, 0, 6, and of course that bottom line stays the same, so we can actually put in those bottom values, 4 and 0, and also this column where the line was drawn. We'd have 11, 2 and 1, and we'd have 2, 5 and 7 there. And again, let's check with our lines. So this time I can draw my lines in the same places, or I can change, it doesn't matter. But I still, this time, only need 3 lines to actually allocate. So again, I need to repeat that process. So I'm going to take away the smallest uncovered number, which again is a 1. Rewrite my matrix so that first column can stay the same. Those bottom values can stay the same. And so can that third column. And subtract 1 from everything that's left. So I've got a 10, a 1 and a 0 there. And I've got a 1, a 4 and a 6 there. So again, let's try crossing out our zeros. And this time I have to use 4 lines in order to do that. So I'm ready to allocate. And I start by looking at which either column or row has a single 0 in it. So I can see here at the bottom, here I've got a 0 there in H and D. So I'm going to allocate that 28. That means this 0 is not a possible allocation anymore. So in row 3, we're looking at column 2. So it gives me that 28 in G and B. Again, gets rid of that 0. When I look up to that first row, E can only do C, so that gives us that one. And finally, that leaves F doing A, task A. So when we add up those 4 values from our original matrix, we end up with our answer as E, 92. Okay, so question 5, looking at a telecommunications company, want to represent the length of cable between the 5 towns, the minimum cable, so we're looking at a minimum cable that's required to link. They're actually asking for a minimum spanning tree here. So we look for our smallest value. We've got a 19, so I'm going to use that cable there. The next smallest number is a 26, so let's use that edge there. And the next 2 are 27, so I can use either. I'm going to use this one here. I don't need to use that second 27 because this vertex here is already connected in, so we don't need to double up. So now let's look at our next smallest number is 28, so we use that edge there. And at this point, we are all connected. Now remember, the other way to think of it is I have 5 vertices here, so I only need to use 4 edges. So once I've got 4 edges drawn in, I should actually have my minimum spanning tree and everything should be connected. So when I add 27, 28, 26 and 19, I end up with my answer A, 100. Okay, this next question here is a minimum cut. So they're just actually asking for what is the capacity of the cut shown. So working from the start, I need to add the 8 because that gets blocked off. I need to add the 6 because I can get through to here and it gets blocked off. And similarly, I add this second 6 because I can get through to here and it gets blocked off. So when I add those 3 values together, I end up with 20, gives me my answer of E. Question 7 asks us for the minimum number of edges for a graph with 15 vertices to be connected. So again, as we said before, the number of edges for a minimum graph to be connected is the number of vertices minus 1. So in this case, that would mean our answer is B, 14. And number 8, the number of vertices for a planar graph. So the key word here is planar. That tells you need to use Euler's formula. So vertice minus edges plus faces equals 2. We know that the number of edges is 25 and the faces is 12, and we need to solve for the number of vertices. So we can either solve that by hand or using our calculator. And we end up with the number of vertices is 15, so our answer is B. Okay, so this next couple of questions relates to the graph shown here, and it requires us to find a critical path. So we're going to have to do our forward and backward scan, and then we're also going to be asked for the latest start time of activity E. So the first thing we're going to do is just do our full forward and backward scan so we've got all the information that's required. Okay, so I've just made that a bit bigger and drawn the boxes on so we can now work our way through. So we start at the beginning. Obviously we have an earlier start time of 0 here. Working up A, we have an early start time of 4 in the box there. Coming down across E, we have 3 paths coming into that vertex 4. So from E, we have early start time of 6. We also need to consider B. That comes directly from the beginning, so that also gives us 6. And F. So let's just go back and fill in the box at 3. So activity C would give us a start time of 5 there. 5 plus 2 means F gives us 7. So biggest number in the box, 7, and we can move forward. Going up to vertex 5, we have path D would give us 8, and part H would give us 10. So we're going to put 10 in the box there. Working down to 7, we can see we've got 2 paths again. So I would give us 16, and let's go back to vertex 6 to get the next value for J. So across G, 5 plus 4 would give us 9 at 6, and then 9 plus 3 would give us 12. So 16 goes in the box there. Now we do our backward scan. So start with 16, same number in the box, and work our way backwards. So going down J to vertex 6, 16 minus 3 is 13. Back across G, we have 2 vertices coming in at 3, or leaving from 3. So we need to consider the path of F and G. G would give us 9, 13 minus 4. We'll go back to vertex 7 and work our way along the other path now. So 16 minus 6 at vertex 5 would give us 10. Travelling down H, so 10 minus 3 would give us 7. 7 minus 2 along F would give us 5. So now we can complete that. Smallest number in the box, so 5 here at vertex 3. And finally back along C. So again at vertex 1 we've got 3 paths that leave from vertex 1. So we have 3 paths to be considered when we're working backwards. So 5 minus 5 at C would give us 0. And working back from vertex 4 up along B, so 7 minus 6, B would give us 1. Now we just need to complete the last couple of boxes. So back up to vertex 5 and let's go across path D. We can see going into 2, there's actually 2 paths again. So D would give us 10 minus 4 is 6, and E would give us 7 minus 2 is 5, 5 in the box. And then finally A, 5 minus 1 would give, 4 would give us 1, so 0 in the box, and we've got all our information there. So question 9 asks us for the critical path. So remember the numbers on the outside tell you which direction to go into. So from vertex 1 we can see the C gave us the 0, so we're actually going to travel along activity C to here. F gave us the 5, so we go up along F, and we can see H is the only option here, so we travel along H and then down I to our finish point. So our critical path there is C, F, H, I, and that gives us our answer of D. The next question actually asks us for the latest start time of activity E. So again, we're reading that from our critical path and from our forward and backward scan information. So if we look at activity E, we're looking for its latest start time, so back at the beginning and the right-hand side. But remember, we should also always check what's written on the outside here. So activity E had a latest start time of 5, whilst D had a latest start time of 6. So it is important to check that information on the outside. And so we can write our answer in now that activity E had a latest start time of 5, so therefore our answer is C. Okay, moving on to a different question, adjacency matrix. So this is another question where they're asking for an untrue statement. So we need to go through the possibilities and work out what the final answer is there. So a loop exists at vertex A. So we have a 1 in the A to A, which represents a loop. So that's true. There is a loop at A. Vertex C is isolated. Now, if we look here where we're going from C to all the other vertices, we can see there's no connection to A, B, or D. C is on its own with 2 loops. So if we were to draw that, we'd have C with 1 loop with 2 loops, but no connection to anything else. So it actually is isolated. So that's a true statement. With these questions as well, if it helps, you can draw the vertex from the adjacency matrix. and that might actually help out with this particular type of question. Option C, vertices B and D are connected by 2 edges. So if we look at from B to D, we have a connection of 2. So 2 edges, multiple edges. And from D to B, same thing, 2. So yes, there are 2 connections there between those 2, so a true statement. The graph is connected. Well, we've just said that C is an isolated vertex. So if something is isolated, then it can't be connected. So that is a false statement. Let's just make sure that option E is a true statement before selecting D as our answer. So there we have the degree of vertex A is 4. So at vertex A, we have a loop, we have a connection to B, and we have a connection to D. So then when we consider the degree of that vertex, then yes, there are 4 different paths leaving it. So that is a true statement at E. So our answer is D. Okay, so question 12 asks us to find the quickest way to travel from each of your friends' houses only once and then back home. So if we're going to houses, that would be vertices, and then back home means we need a circuit. So to travel every vertex only once and then end up where we started from, we're looking for a Hamilton circuit there. So our answer is B. Question 13, we want again to look at which statement is untrue. Sorry, which statement is true. So let's work our way through. The graph can be redrawn in planar form. Well, yes, it can. So that is true. The graph is complete. Now, note with a complete graph, it's talking about a connection between each vertex and every other vertex, but there is only one edge, so there can't be any multiple edges with a complete graph. So that means that statement is false. An Euler circuit exists. Remember, for an Euler circuit to exist, you have to have all vertices of an even degree, and we have at the moment in this graph 2 vertices that have an odd degree. At the top there, that has a degree of 3, and the bottom, we have a degree of 5. So that's a false statement. The sum of the vertex degrees is 21. So in order to work that out, we need to find the degree of each vertex and add them together. So we have 3 at the top, we have 4 on the right, we have 5 at the bottom, and 4 again. And that gives us a total of 16, not 21, so that's a false statement. And finally, no Hamilton path exists. Well, I can make a Hamilton path just by simply going around the outside here, and that's a Hamilton path, uses every vertex. So that is also false. It means that A was our correct response there. Always remember to check all the possibilities, because it may just be in your haste to finish a question you've actually misread it. Okay, question 14, how many edges does a minimum spanning tree with 18 vertices? So just like before, if we have 18 vertices, to make it a spanning tree, we need 1 less edge, so we just need 17. So our answer is A. Okay, question 15. Activity C has an earliest start time of 6, a latest start time of 9, and a latest finish time of 16. How long does it take to complete activity C? Okay, so let's draw this out so we can understand what's going on. So I've got an activity C that lasts for some unknown time. I know from the information given that I have an earliest start time of 6 and a latest start time of 9. This latest finish time talks about where C finishes the latest, so therefore the right-hand side of the box, so that I have a 16 there. Now by doing my backward scan, I know that this number 16 minus the duration of the activity gives me the number that goes here. So in order to get 16 minus something equals 9, that means C had to take 7. So our answer there is B. Okay, so question 16. A graph has 5x plus 5 vertices. It has 4 minus 5x faces. How many edges does it have? So whenever you're given those 3 keywords or anything about Euler's formula or a planar graph, that tells you that you need to use the formula vertice minus edges plus faces equals 2. Now in this case we don't have values, we've got little expressions. So we're just going to do the same thing though. I know that 5x plus 5 is the vertices minus the number of edges plus faces for minus 5x has to equal 2. Okay, so from that we can either solve that by hand or just simply put it into our calculator using our solve function, where we've solved for e and we end up with e equals 7, which gives us the answer B. Okay, so question 17, another one where it's asking for untrue statements. So again, be careful and read through the statements carefully. So option A, the graph is connected. Well, that's true. We have no isolated vertices. All vertices have a degree of 3, and we can see, yes, when we run around and count those, we have all have a degree of 3. The graph is planar. It is. There's no intersections where there is no vertices, so it is currently planar. The graph has no multiple edges. Correct, there are no multiple edges there. Everything has just a singular connection between them. And the graph has no circuits. Now, I can make a circuit anywhere, in lots of places on the graph. So that is a false statement. So therefore, our answer there is E. Okay, so 18, I've already posted some solutions to that, saying that basically we have no solution in the options there, and it was one that we actually deleted last year. So just looking at our answer that I've given you there, that would be the adjacency matrix. Remember, where you've got the loop at C, it is only counted as a 1. Okay, question 19. So here we're looking at, for the graph, form an Euler circuit if an edge was to be added between which two vertices. Now, to get an Euler circuit, we know that there has to be no odd vertices. So let's just check. P is even, Q is even, R is even, S at the moment is odd. It has a degree of 3. T is even, and U also has a degree of 3 and is odd. So in order to make a circuit, an Euler circuit, we want to add another edge between those two odd vertices. And if we were to do that, you can see now the degree of each becomes 4 and an even number. So we always want to add between the two odd vertices where possible, and that gives us our answer of E. Okay, question 20 is another maximum flow question. So again, use the ends as a baseline. That cut would give me a 19. This end, I would end up with 21. So already too big. 19 is the number I want to beat. And you'll notice that is there in the answers. But we can see they've given us 11, 12 and 16 as other possible answers. So let's see if we can get one of those. If I was to cut through the middle here, working from the start, I add the 12 because it's get cut off, but nothing will get to that edge with the 8, so it doesn't need to be added. Across the top, we can get to the 4, so we add those, and that gives us 16. Now, looking at the rest of the graph, we can see if we can get a number of 11 or 12 as a cut, but it's not possible from this graph, so our answer is actually C, 16. Okay, so we have an allocation question here, which is a little bit different because we're not actually needing to minimise anything. We're just seeing, can you understand the information given in the bipartite graph? So 4 family members have picked or allocated their preferred types of accommodation. So let's just read through the questions, the options, and decide which is not true. So camping is the most preferred option. We can see it has 3 people selecting it and the others only have 2 or 1. So that's true. It is the most preferred. Steve prefers to stay in a youth hostel. So Steve has a connection to the youth hostel. No, he doesn't. So that is false. But let's just check the rest to make sure. So staying in a hotel is the least preferred option for this family. And yes, the hotel is the only one with 1 preference. So that is a true statement. Mari does not prefer to stay in a bed and breakfast. So Mari has selected camping and youth hostel, but not bed and breakfast, so that's true. She does not prefer to stay there. Charlotte likes more accommodation options compared with the other family members. And as we can see here, Charlotte has selected 3 different types, whereas the rest have only chosen 1 or 2. So that is also true, meaning that our option B was our correct answer there. Okay, the sum of the degrees in the vertices in the graph shown. So work out the degree of each one. So 2, 1, 2, 3, 4, 5. Remember, a loop counts as 2. 1 out here, 2, 4, and 4. And so we just need to add those values together and we get 18. So our answer is D. Okay, question 23. So, network connecting country towns where the towns are shown as vertices, the roads, and edges. We want to find a path that goes to every town and ends at a town other than the one we started. So, every town means every vertex, so we want a Hamilton type. And we want to start and finish in 2 different places. So that only requires a path, not a circuit. So therefore our answer is C, a Hamilton path. Okay, question 24. So another allocation problem. We want to cost getting a taxi for 4 healthcare workers to visit 4 different destinations. We need to work out who should go where in order to minimise. So we need to work through our Hungarian algorithm again here. So first step, subtract the smallest number from each row. So 13 in the first row, 16 in the second, 12 in the third, and 17 in the fourth. So let's just write down our answers there. That would give us 8, 0, 3, 17 in the first row for Erin, 0, 10, 0, and 6 in the second row, 0, 6, 10, and 5 in the third row, 2, 0, 10, and 1 in the fourth. Now, I don't have a 0 in every row and column, so I'm going to continue with the next step with my column reduction. So, smallest number in the first column is 0, so nothing changes. Second, again, 0, nothing changes. Third row, 0, nothing changes. And finally, I'm going to subtract 1 from that last column. So, my values stay the same in the first 3 columns, so we just rewrite those, and 3, 0, 10, and 10, and we're going to subtract 1 each from here, so 16, 5, 4, and 0. Now let's check with the lines. Remember, I need to use the minimum number of lines possible to cross out all the zeros. So it doesn't matter where you start from, but try and see how many lines you need to use. Now, I can already see after using 2, I'm going to need to use 4 to actually get all of those zeros. So I'm ready to allocate. Okay, so the top row, there's only one option there for Erin. She has to go to Barden. So we can look at our answers and cross out D, B, and C as possible answers. So we're left down to only 2 options now. That would mean in this bottom row, Naomi has to go to Dunley. So looking at the 2 options left, we've got Naomi to Albin, Naomi to Dunley. So that's our only option left, A. Now we can go through and do the rest of the allocation to make sure. And we can see that Jake can only go to Albin, and that's correct for what we've been given in that option A, and which leaves Milo at Catbill, which again is correct there, so A is our answer. Okay, another minimum cut, maximum flow. Now this is quite a tricky question. It's not as straightforward as you might first think. So you need to make sure you're reading the question carefully. So the question says, from the 2 cuts shown on the network flow diagram, we can conclude that the maximum flow, so it's just the maximum flow from the 2 cuts. So let's look at the 2 cuts here. Cut 1 would give us a value of 37. Cut 2 would give us a value of 23. So at the moment, 23 is our smallest value. That doesn't mean that that's necessarily the minimum cut. What it means is that at the moment, that's our baseline, that's our number to beat. So if we were actually to find the minimum cut, already I can see that if I was to draw a line through here, I would get a value of 21, which is smaller than 23. So we can see that from the answers, our maximum flow is not 23, but cannot exceed 23. We know that it's not bigger than that, but we don't actually know what the answer is based on the two cuts that have been given us. So that's a really tricky question in terms of the wording of the question, okay? And that's worthwhile sort of looking at and making sure that you understand how that question is interpreted in that way. Okay, so that's it for the multiple choice questions. I'll put up a different video for the extended response, but those answers are already available as well. Hopefully this has been helpful. Let us know if you've got any questions.